Hi, everybody. Hope that you guys are doing well. Today is Monday the 9th. I've got, yeah. Um, what we are going to be doing today is we're going to be concluding our kind of demonstration of inhibition patterns. I'm going to walk through those and show you some basically what you should expect in terms of um, questions that you might be asked and how to understand enzyme inhibition. I wanted to make an announcement about Wednesday's class. I am going to have Wednesday be a pre-recorded lecture, so I'll have that done before your class on Wednesday. But I want to go ahead and set aside that time on Wednesday for basically, a focused question and answer session, a review session of sorts, because that is meeting number 15. Can y'all hear? Can anyone hear? Can anyone confirm that they can hear me? I can. I am able to hear. Okay. Um, okay, so I'll try to project as much as I can. Um, but Wednesday is going to be a review session. If you don't have any questions, you don't have to join our regular record or our regular Zoom session. I'll go ahead and record it. Um, and post that recording on our Canvas site. I'll come with some kind of material and sorts of questions to consider. Um, but I think that it's a really kind of good and easy opportunity for me to give you guys hopefully a little bit more value and hopefully a intentional um, review time. So that is what Wednesday is going to be. But in the event that you miss that, or you miss sorry, if you miss that, I will record it, but also the lecture or the content that we will be covering on Wednesday will be up before that class period. Um, and then after that, you have a break for a week. So I hope that you plan on doing something relaxing for your spring break. Our next exam isn't until the 1st of April, though, correct? Yep, that's right. The next exam is April 1st, right? Yep. I can hear now. What did you say was on Wednesday? Review session. Uh, sure thing. So that's kind of the plan. Um, there will be content on Wednesday, but like I said, I'm going to post that before that class period. Um, so it's kind of like I'm trying to get the most out of Wednesday's meeting as possible. So I'll treat it as a regular lecture section, but also we'll reserve a review there. Okay, so I am going to go back to the beginning when it comes to inhibition. In the event that you hear some enthusiastic hollerings, one of my kids is homesick from school, and so he's been playing a video game. So at any rate, if you hear that, that's what that is. Okay, so inhibition. Um, enzyme inhibition. I talked about this last time, but now we're going to go into the different models. So inhibitors are important for a variety of different reasons. They can help you explore and learn different things about an enzyme, the shape of an active site, in addition to the shape of the active site, um, the amino acids that make up the active site. Um, so they can be used to gain information about the actual mechanism. So what are the steps that are taking place? They can be used to gain information about the regulation or control of the metabolic pathway, and they're very important in drug design for all the reasons listed above. Now, enzyme inhibition. Typically, when we talk about inhibitors, we're talking about reversible inhibition. Now, reversible inhibition is done by a reversible inhibitor, something that binds to an enzyme to inhibit it, but it can be released. So I always use a Pac-Man type of figure to demonstrate an enzyme. or yeah, there's my enzyme, and an inhibitor is going to bind. So we've got the inhibitor is bound, and you can kind of go back and forth. You reach an equilibrium there. Now, an irreversible inhibitor is a substance that's going to cause inhibition that cannot be reversed, and typically that's going to be involving breaking of a covalent bond. Now, inhibition patterns, these three or four, you might say, are the ones that are going to be the most common. Now, when it comes to these different models, there's a couple of different graphs that we are going to look at. So if you remember last time we talked about a graph that looks like this, or the last two class meetings, where we have the y-axis that represents the rate of a reaction versus your substrate concentration. This graph styling is typically going to, well, for many enzymes, you're going to see data plotted that looks a little bit like this. This is a hyperbolic curve, but the axes here represent a graph that is demonstrating Michaelis-Menten kinetics, where you can get your important parameters, the Vmax and the Km, from this. Now, sorry, just one second. As you can see, this is a hyperbolic curve. This is not observing a linear change. Now, what we can do with this data, and what will be very important for our study of enzyme inhibition patterns and enzyme or graphing an enzyme's activity, is to look at what's known as a Lineweaver-Burke or an LB or a double reciprocal plot. Now, a double reciprocal plot takes the data that you use for a Michaelis-Menten curve to make the y-axis and takes the reciprocal of that. So the reciprocal of V would be 1 over V. Give me a 5 in the chat if you follow that. Okay. Okay. So then the y-axis, so y-axis or data used to make the y-axis of MM plot. Whenever I say MM, I'm referring to a Michaelis-Menten plot. The data used to make the y-axis of an MM plot, well, you take the reciprocal of that to make the double reciprocal plot's y-axis. So our y-axis is 1 over velocity. Now, the x-axis of a Michaelis-Menten plot is your substrate concentration. And for a Lineweaver-Burke plot, your x-axis is going to be 1 over substrate concentration. So essentially, the data that you use to make one of these plots, where I'm going to put a big star, oh wow, thanks PowerPoint, that's much better than my drawing, that you're going to use to make this plot, you can take that same data, take the reciprocal of it to make a Lineweaver-Burke plot. Now, one of the big differences between a Michaelis-Menten plot and a Lineweaver-Burke plot, or a double reciprocal plot, I'll use these two terms interchangeably, is that when you talk about a Lineweaver-Burke plot, you're not just going to use, whenever you graph something, you have the first, second, third, and fourth quadrants. Well, for a double reciprocal plot, you're going to use quadrants 1 and 2. So your x-axis will be a negative. It will go from negative infinity all the way to positive infinity. Okay, so it's pretty standard practice to look at a Lineweaver-Burke plot that looks like this. 1 over velocity versus 1 over substrate concentration. Okay, so like I said, this one on the left-hand side is a Lineweaver-Burke. or Lineweaver-Burke plot, BU arcadule. How's that? Lineweaver-Burke or a double reciprocal. Reciprocal. And if you're thinking double reciprocal, that's an interesting name. Where did that come from? Well, one, two, two reciprocal values are used to plot that. Okay, so these are the two plots that are going to be most important for analyzing enzyme inhibitors. We're going to get to those in just a little bit, but I want you guys to have that sort of background information because more times than not, when we're talking about inhibitors, we'll be looking at a double reciprocal plot. Now, there are a couple of different patterns, major patterns for enzyme inhibition. They are represented with all of these different models. This one, this one, this one. Now, the first one, which we talked about last time, is demonstrated by a competitive inhibitor or competitive inhibition. In a competitive inhibitor, you have your enzyme that basically has an equal chance to bind a substrate or the inhibitor. Kind of flips a coin. Which one is it going to bind? If your enzyme binds the inhibitor, it will not simultaneously bind the substrate if that inhibitor is a competitive inhibitor. You will form a complex of the enzyme plus the inhibitor. Now, that means that that substrate is just kind of left to languish and to flounder around. If the enzyme binds the substrate, well, then you'll form a complex known as the ES complex, the enzyme substrate complex, in which case your enzyme will not be binding the inhibitor. Now, you could kind of think about this because, well, both the inhibitor and the substrate are trying to access the enzyme in the exact same location. So how is that going to happen? More than likely, you're going to have a natural substrate and an inhibitor that look similar to one another. So as an example, the enzyme known as succinate dehydrogenase, its natural substrate is this molecule right here, succinate. We've got two carboxyl groups on it. Okay, it's a total of 4 carbons long, but carboxyl group are also found on both ends of a molecule known as malonate. Now, succinate dehydrogenase, if it is looking for a molecule that has a series of carbons and 2 carboxyl groups, and it sees succinate, it's going to say, great, that's my natural substrate. I'm going to bind that molecule and I'm going to catalyze a reaction to produce this molecule here known as fumarate. But imagine that the enzyme's squinting its eyes and it's like, I'm looking for 2 carboxyl groups. Oh, there they are. And it binds malonate. Well, it's not going to be able to catalyze that reaction. Malonate functions as an inhibitor for succinate dehydrogenase. In which case, what's the enzyme going to do? Well, it's not going to be able to catalyze a reaction. It's not going to be able to produce fumarate. It's going to hold on to that inhibitor, and then if it can, it will release it, and then it will try to go back to the drawing board and bind succinate. If it binds succinate, great, it can move on, catalyze the reaction, and make fumarate. Now, this is one of the reasons that these two substrates are sorry, this substrate and the inhibitor are competing for the same spot on the enzyme. Now, when it comes to understanding competitive inhibition, a competitive inhibitor reduces the amount of free enzyme available for substrate binding, thus increasing the Km for the substrate. So what that means, an increase in Km. Let's think about magnitude of Km. A small Km means high affinity. A large or a larger Km means lower affinity. So what a competitive inhibitor does is it tricks the enzyme. A competitive inhibitor causes the Km to go up, which results in a decrease in enzyme affinity for the substrate. So if you think then about Km, okay, so let's go back and let's just think about Km for a minute. And let's remember our definition for Km. Km is the amount of substrate needed for enzyme to reach. Does anyone remember what to reach what in terms of the reaction rate? Our definition here. Km is the amount of substrate needed for the enzyme to reach. How about, it's not quite Vmax, but Vmax over 2. 50% max velocity. Great job, Miles. Absolutely right. Okay. So now let's imagine we have a Km, or sorry, let me rephrase that. How's how's everyone feeling about this? Is it like, okay, yeah, I remember that. If you remember it and you feel solid about it, good. If you're still trying to wrap your mind around that, give yourself some patience. I'm sorry that I don't want to sound bossy. Just it is kind of a weird thing. I I think that it might be helpful to try to think about like an analogy or something that works for you. And I'll revisit that on Wednesday. But for right now, I want to apply some numbers. Let's say that we have an enzyme with a Km for its substrate of 0.1 millimolar. Okay. Then if you give that enzyme 0.1 millimolar substrate. Okay. So now I'm going to go to these numbers. We've got our enzyme and it has a Km of 0.1 millimolar substrate. So what that means is if you give this enzyme zero point 0.1 millimolar of the substrate, the enzyme is going to catalyze the reaction. So I'll say enzyme does reaction at a rate of Vmax divided by 2. Okay. So now let's apply this situation. We give our enzyme exactly 0.1 millimolar of the substrate. How fast is the enzyme going to catalyze the reaction? Well, it's going to catalyze it at half of its maximum velocity. Okay. Now let's imagine that we have an inhibitor. And this inhibitor causes, and why at half max velocity though? Can it ever do its maximum velocity? That's a great question. So the half maximum velocity is just kind of a, a basis for comparison. So the maximum velocity is something that's kind of theoretical in a sense. It's speculative based upon these particular constants, based on the empirical data that's been collected on that enzyme. So the half maximum velocity is just kind of I guess, for lack of a better phrase, it's almost like an industry standard in some respects. I hope that answers your question. Um, okay, good. So now we're going to give this enzyme, or we're going to give this enzyme an inhibitor, and it causes the Km to go up to 0.5 millimolar. Okay, so the Km goes up to 0.5 millimolar. So what does that mean? That means that we need, or let's say enzyme, our enzyme needs more substrate. Not just in general, but it needs more substrate to reach half of its Vmax. So essentially, another way of putting that is your enzyme, or sorry, your inhibitor causes Km to go up, which in effect says your inhibitor, I'm going to put a semicolon, causes the enzyme's affinity, AFF, for the substrate. Does it cause it to go U for up or D for down? Add to the chat. What does your inhibitor cause the enzyme? Causes the Km to go up. It causes the substrates or the enzyme's affinity for the substrate to go down.
That the PS5 is controlled by.
That's crazy, buddy. Use a different one. I'm sorry. Help you right now.
Channel parts of their.
Okay. So this is what a competitive inhibitor is going to do. It's kind of going to, it's almost going to trick the enzyme into saying like, hey, you don't really want to bind that substrate because it's going to cause the Km to go up, decreasing the enzyme's affinity for the substrate. Now, what that means is, well, can the enzyme ultimately get back to its half of maximum velocity? Can it get there? Yeah, it can. How do you do that? Well, with a situation like this, you add more substrate. The enzyme is allowing the substrate and the inhibitor to compete for the active site. If you give more substrate, the chances that the enzyme will bind the substrate are going to go up, in which case you're going to be able to catalyze the reaction. Okay. Now, when it comes to our kinetic parameters, what's really important to understand is what do we care about when it comes to competitive inhibition or any type of inhibition? We have two major kinetic parameters. We have Km and Vmax, the maximum velocity. Okay. So what does a competitive inhibitor do? It causes the Km to go up. Your Km goes up, therefore, your enzyme has a lower affinity for the substrate, and it takes more of that substrate to get to half of maximum velocity. Now, what I want you to notice right here, these graphs on the left, these graphs, or sorry, this graph on the left-hand side, this is our Michaelis-Menten plot. Now, if this graph were to basically, if the x-axis were to go on into infinity, I'm talking about affinity, but now I have to mention infinity. So naturally, the way that I spoke when I was like 7 comes back to me. Um, this line right here will slowly but surely, with enough concentration, as our x-axis goes on, this will continue to rise. So too will this. So too will this. All of these values, all of these curves will ultimately meet up with one another. And the reason for that is a competitive inhibitor. If we go back just a second to this right here, A competitive inhibitor will delay or impact the formation of ES. But as soon as that enzyme substrate complex is formed, the enzyme is basically acting right here, converting the substrate into a product. And the enzyme does not get slowed down at all in that phase. So what that means is that your Vmax remains unchanged. Some people will write that as an arrow like that, or they'll just write a dash, or they'll just, make sure that they don't get any confusion there, and they'll just say it's unchanged. So your Vmax is unchanged. Your Km will go up, but your Vmax will be unchanged. Now, that's what this will look like on a Michaelis-Menten curve on the left. On the right, the best way that you can tell on a Lineweaver-Burke plot, which here I'm going to highlight my axes, one over velocity and one over substrate concentration. What I want you to recognize is that this blue line represents the enzyme and the substrate. So a series of trials were done, the enzyme and the substrate. This blue line right here corresponds to this olive colored line right here. So when there's no inhibitor. The green line in my Lineweaver-Burke plot shows plus inhibitor. It's not stressing the concentration of the inhibitor, but it's just indicating that some inhibitor was added. That corresponds to this blue line right here. There is some inhibitor present. Last but not least is this +2 with the inhibitor in parentheses. Okay. And I'm going to come back to your question. I see a question in the chat. This corresponds to this purple line right here. So basically 2 times the inhibitor concentration. Sammy asks, so are you saying that this inhibitor will initially delay the formation of ES, changing the initial rate of product formation, and then when it is released, the normal enzyme activity will continue to speed up this reaction? So it's the rate of E and S, but in terms of any sort of bonds being made or broken, as soon as that substrate is there, that will not be impacted. So delay the formation. So to answer your question, rather than talk backwards, will initially delay the formation of ES, changing the initial rate of the product formation. And then when it is released, the normal enzyme activity. Yes. Yes. Okay. So when it comes to graphing this, well, what I want you to recognize, and I think that with all of these graphs, specifically the Lineweaver-Burke plots, I think that it's best to recognize the patterns of the no inhibitor, which I'm going to write this as unchallenged, versus the challenged samples. So the presence of the inhibitor. Now, if somebody's studying an enzyme and studying an inhibitor, it's pretty common to try the addition of multiple or to increase the concentration of an inhibitor, which is why we have this data set and this data set. But what I want you to take away from this is let's just look, let's just focus in on and compare the blue line right here and this sort of purple line right here. The blue and purple lines will intersect on the y-axis. So intersecting on y-axis. Now, the lines here, this blue line or the purple line, all these lines will have, or will, since it's linear, they can be plotted using y equals mx plus b. So whenever you graph this data, you would get an equation for your line of best fit, and that equation would be in the form of y equals mx plus b. Now, this intersection right here, let's see. Hmm. Um, if I were to ask for coordinates, x, y coordinates for this intersection, would everyone agree with me that, we're looking at an x value of approximately 0 and a y value of, let's call it 5? Could everyone give me we'll go with a 5 in the chat if you agree with that. Great. Now, we've got a 0 and a 5 there. So then our y-intercept. This is one of the places where people get a little bit tripped up. Your y-intercept is equal to 5. Does everyone agree with that? And then that y-intercept is also equal to 1 over v max. Now, it's been a minute since I've been in algebra 2, I think. Maybe it was algebra 1, where you learned about the transitive property and the associative property. I'm bringing that up because we have these two statements. Y-intercept is equal to 5. Y-intercept is equal to 1 over v max. So based on this, I can say 5 is equal to 1 over v max. Could everyone give me a 9 in the chat if, oh yeah, I agree with that. I see that. I see that graphically. Okay. Now, the reason that I bring that up is because, oh, I got it, 8.5. Okay. Um, because what we want to do is we want to use this graph, this Lineweaver-Burke plot, to calculate our Vmax and calculate our Km. Now, one of the things that people have a tendency to do is they look at this plot and they say, aha, 0 and 5. Okay, cool. What's my Vmax? My Vmax is 5. Incorrect. Because they've taken this and consolidated it down. They've simplified it too much. Your y-intercept is equal to 1 over Vmax. So your y-intercept here is also equal to 5. 5 is equal to 1 over Vmax. Based on that, your Vmax is equal to 1 over 5. Your Vmax is equal to 0.2. Now, I haven't defined units here. I don't want you to worry about that at this point, but I hope that you guys can follow all of that and track that, because that's one thing that I want you guys to be able to do. Now, the next part, we've got two kinetic parameters that we're most interested in. And I'm going to duplicate this slide so I can I can highlight everything except for that. Yeah. Nope, too far. Here we go. Now, my x-intercept is equal to negative 1 over km. What do we know about our x-intercepts in terms of their value basically here? Well, they range from 0 all the way to negative infinity. So those values are going to be less than 1. They're going to be or less than 0. They're going to be negative values. So let's take our Km right here. This is our dashed line representing our dashed blue line representing our unchallenged setting. And let's say let's say that's negative 5. Now we're comparing that to our purple line right here. Let's say that's negative 2, just for giving ourselves nice round numbers. So I'm going to say, based on that, when there's no inhibitor, well, x-intercept is negative 5. Negative 5 is equal to negative 1 over km. Could everyone give me a y in the chat, just the letter y in the chat, if you follow how I jumped to this right here? Great. Now I'm going to erase the y and I erase the big circle because this is our mechanism to determine that, well, heck, this is a negative value. This is a negative value. They're going to cancel. So effectively, it's the same thing as saying, well, 1 over km is equal to 5, or 5 is equal to 1 over, Joel, km is equal to 1 over 5, or km equals 0.2. Now, compare that to this purple line where it's -2. So our new x-intercept, I'm going to say our challenged, is going to be -2. Okay. Now, our x-intercept, again, is equal to -1 over km. -2 equals -1 over km. And rearrange that. And I end up with km is equal to 1 over 2. I dropped the negatives. I came up with that right there. So km is equal to 0.5. What happened to my km? It went from 0.2 and it went up with a competitive inhibitor. Now, the way that I think is helpful to remember this is to think about, what does this graph look like? What does my Lineweaver-Burke plot look like? Well, I've always just or not memorized it, but the mnemonic, the tool that I use is I always think about, there's an X, there's a competition. And the reason that I think about that, honestly, is because back in the early 2000s, there was a football player for the Kansas City Chiefs. He would score touchdowns on punt returns, and at the end of that, he would run back into the end zone, and then he'd do this, and he'd throw an X up. His name is Dante Hall. He played for Texas A&M. He got thousands of dollars worth of parking tickets when he was a student at Texas A&M because he would park wherever he wanted. But at any rate, for some reason, what has stuck in my mind for nearly a quarter of a century is, I think about X. I think about that line, the intersection right there along at my y-axis. You don't have to think about Dante Hall. If you want to, great, Dante Hall, and I would be pretty pumped about that. But if you just look at this and you say, oh yeah, that's what a competitive inhibitor looks like, or that's what competitive inhibition looks like, I'm good. I know exactly what's happening. Then more power to you. Now, with that, that's how a competitive inhibitor is going to impact an enzyme's activity. The Km goes up, Vmax unchanged. Now, in the process, what's happening? Well, it's helpful to think about what are the kind of complexes that can form. EI can form, ES can form in the presence of a competitive inhibitor. Sorry, would you mind explaining just once more? Competitive inhibition could be used comparing both X and Y intercepts. So the X-intercept, let me go down here again. Okay, here's the first slide. When you're looking at the intercepts, that's a great question, Natalia. Whenever you're looking at the intercepts, what you want to do is you want to say, okay, is there a change? Do my data points, does my unchallenged data and my challenged plotted data, do they intersect? So is there intersection section on y-axis? If you ask this question of yourself, and the answer is yes, then what you would say is you would say competitive inhibition. Okay. Now, the x-axis gets a little bit more complicated. What exactly does the +2 mean for the challenged data? Is it just two inhibitors? It's a great question, Anna. Really what this is doing is, if you look at the green line, this is just saying, hey, inhibitor has been added. And then the purple line, the +2 with the inhibitor in the parentheses or the brackets there, is just saying extra inhibitor has been added. So this is really just trying to illustrate that this hypothetical inhibitor has a compounding effect. When you add more of it, it causes more of an impact. Does that help? Okay, cool. So when you ask yourself the first question, is there an intersection of my data on the y-axis? If the answer is yes, then you have a competitive inhibitor on your hand. If the answer is no, then you don't have a competitive inhibitor on your hand. Now, when it comes to the x-axis, if you ask, you can't really ask the same question to get to a competitive inhibitor, but you will, as we go through the different models of inhibition in different plots, you'll be able to ask similar questions. Now, with that in mind, I always think that it's helpful to take a x and y axis and come up with a simple plot. And here's my x and y axis. Here is my no inhibitor data. And before we do anything really elaborate, all that we've talked about is a competitive inhibitor. And I've got this awesome space ink pen, and I drew that line. Okay. My first question, do I have intersection of my data points? So this is plus inhibitor. Do I have intersection on my y-axis? So do these two lines, do I have an intersection there? I don't. So at this point in time, what can I say? Okay, well, if you told me, hey, this is plotted data from inhibition studies, I'd say, okay, that's cool. Well, all that I can say right now is this is not a competitive inhibitor. Can I say more than that? Not right now. But based on this, I could say not a competitive inhibitor. If you showed me this, however, X and Y axis, and we did, here is my no inhibitor. And then again, my data plotted like this. Oh, aha. Yeah, I've got intersection. Actually, wait, oopsies. Oh, if I gave you something like this. Oh, do I have an intersection? I do. So what type of inhibitor is this? That's a competitive inhibitor because if I go through and I calculate my Km value, my Km went up, my Vmax stayed the same. Now, these are going to get a little bit more involved and complicated. Now, but the next one that I want to go to is this right here, an uncompetitive inhibitor. Now, with an uncompetitive inhibitor, you have a type of inhibitor that binds the enzyme substrate complex, but not to the free enzyme. So ES or E plus S produces ES. And when you have that enzyme substrate complex, that's when the inhibitor says, okay, cool, I'm interested in binding. And at that point in time, you can form the ESI or enzyme substrate inhibitor complex. So, things to note here. One is no EI is formed. Okay. The second thing is that when ES forms, just the formation of ES does not mean or does not assure product formation. Okay. So when it comes to this ES not assuring product formation, you have to think that's probably going to impact the Vmax. Now, when it comes to the formation of ES, that might impact Km, but how might it impact Km? So, whenever you look at inhibition patterns, I think it's important to know the complexes that form and the way that the different kinetic parameters will be impacted. So here's a little bit more detailed model of an uncompetitive inhibitor. Keyword is, or the key prefix is un. So an uncompetitive inhibitor. When that ES forms, that's when the inhibitor can say, oh, I'm ready to join. Okay, cool. We formed the EIS or ESI. It's the same thing. Don't get mixed up there. Now, what that's going to do is cause the Vmax to go down. Now, if you look over here, or look at the bottom, where I've just drawn a star, and compare that to this spot right here, free enzyme plus substrate. If you remember when we talked about a competitive inhibitor, one of the strategies to overcome or to offset a competitive inhibitor was to just flood the system with more substrate. Okay? Because after all, our enzyme is competing or is allowing the substrate and the inhibitor to compete. And so if you give more substrate, if you give more substrate, your chances of ES forming are considerably higher. But with an uncompetitive inhibitor, we have no issue with ES forming. ES forms gladly, just like it did in an unchallenged system. So the enzyme substrate, ES forming, is not impacted by an uncomp inhibitor. Now, I want to show you what this looks like graphically on a Lineweaver-Burke plot. So my axes, my y-axis and my x-axis, respectively. My minus inhibitor, so this is unchallenged. So no inhibitor present. Okay, and then inhibitor. The plus I. So that's the same as the plus I bracketed. It's just saying that inhibitor is present here. Now, the first thing that I want you to notice is that this y-intercept, they're not the same. So one good way to look at that is, aha, well, based on where these two data sets intersect my y-axis, these are different. They are different. Therefore, Vmax differ. Then we can look at our x-axis and our x-intercepts here and here. And oh, well, they're different. And so, yeah, Km will be different. Now, when it comes to Km or Vmax, and looking at these plots, I think that it's always helpful to put a number in. I think it's helpful to say, okay, well, let's call that 4 and let's call this 7. And you can do that and you can come up with what the Vmax is. But you can also look at these numbers to come up with a statement. How does the Vmax differ? We know that it differs. Well, does it go up or does it go down? Well, in the unchallenged system, so when there's no inhibitor present, it's at this level. Then in the presence of the inhibitor, it's here. Okay. So that number, that raw number, that the raw magnitude of that number goes up from, the examples I gave it a moment ago were 4 and 7 respectively. But to put it another way, it increases. Now, these are reciprocal values though. So if this is 4 and this is 7, the Vmax goes down because whatever this number is 1 over Vmax. So if it increases, then your Vmax is going to go down. Is everyone solid on that? And again, like I said, it's helpful to plug numbers in and say this is 4. Just give yourself a round number. This is 7. Okay, so 7 is equal to 1 over Vmax. 4 is equal to 1 over Vmax. Solve for your initial Vmax in the unchallenged system, that would be 0.25. And then solve for Vmax here in the presence of an inhibitor, 1 over 7 would be something like, that'd be 0.14 or something like that. Does that make sense that your Vmax goes down graphically and mathematically? I like to say mathematically. Could you give me a 1 in the chat if, okay, I follow Vmax. Okay. Now, if we look down to the x-axis in the x-intercepts, how does our Km change? Now, what I think is helpful is to, again, plug in numbers. You know that they're going to be different, but think about this in terms of, well, what's the magnitude of this number? If this is 2 and this is 4, what does that mean? And yes, this is a -2 and this would be a -4, but I want you to look at the absolute value just so you can provide the statement. Does your Km go up or does your Km go down? Well, set this equal to -2, and you're going to end up with Km is equal to 1/2. Set this equal to -1 over Km, and you're going to end up with Km is equal to 1 over 4 or 0.25. When Km equals 1/2, 0.5. Okay, so what happens here is an uncompetitive inhibitor causes the Vmax to go down, the Km2 goes down. Does that make sense? Give me a Y or N to the chat. And let's just think about this number-wise. Now, I think that there's always a place that this seems like, and I mean, I think that it's always common to look at the inhibitors and think and ask the question, well, which one's the best? And there's not really one type of inhibitor that's better than the other. I think that for different purposes, they have different applications. But if you think about this right here, Vmax goes down. So an uncompetitive inhibitor is kind of like the brakes. It slows the enzyme's reaction down. The Km, well, the Km goes down. The Km goes down. Wait a minute. That kind of sounds like a good thing because if the Km goes down, then the affinity goes up. Are the formulas both on the x-axis and y-axis saying that? Well, this right here is, and this right here is. This right here and this right here we haven't gotten into. That's about the affinity of the or the enzyme's affinity for the inhibitor. Don't worry about that right now. Right now, I just want you to be able to look at an uncompetitive inhibitor or competitive inhibitor graph and deduce and calculate the Km and Vmax respectively. No worries, don't apologize. It's okay. Um, so if the Km goes down, that means the enzyme's affinity for the substrate goes up. Isn't that a good thing? Well, not particularly. It's not that black and white that yes, it's good and yes, it's or no, it's bad. Um, you got to remember one part of this is that the reaction is slowing down. So that is one, excuse me, one aspect of the, or one part of the equation and one part of the system. But then also, I think a fair question is why? Why is that happening? Well, what's happening here is your enzyme is basically being sequestered as a part of this EIS complex in the presence of an uncompetitive inhibitor. So that means the amount of enzyme is kind of going down. Because if you think, let's say there's 100 copies of the enzyme, and let's say 20 of them end up here after one round of the enzyme catalyzing reaction. In round two, you're not starting with 100 copies of the enzyme, you're starting with 80. Then you've got this kind of mixed round where, again, the number of enzymes is going further and further. And so that enzyme's concentration relative to the amount of substrate, well, the enzyme's concentration is just plummeting, but the amount of substrate by comparison, relatively speaking, is just skyrocketing. Okay, Now, the last type of inhibition that I want to talk about is on this slide right here. It's listed as a mixed inhibitor. Now, you will see a mixed, you will see it referred to as a mixed slash non-competitive inhibitor. Competitive. We will talk about both of these and why they're grouped together. When we talk about a mixed or competitive inhibitor, I want you to look down here in this schematic. In this schematic, we have our enzyme that can bind the inhibitor or combine the substrate, leading to the formation of this EI complex. Now, this, I'm going to highlight it actually. This I right here, that free ends or that free inhibitor is capable of binding the free enzyme, leading to that EI complex. That free inhibitor is also capable of binding to ES, leading to the formation of ESI. So this is an inhibitor that has kind of multiple functionalities. It can bind the free enzyme, it could bind the enzyme substrate complex. Which one it ends up binding might vary a little bit. And that's where we come into this difference of a mixed inhibitor versus a non-competitive inhibitor. Now, when it comes to a mixed or non-competitive inhibitor, what I want you to look for, sorry, I jumped ahead, is when it comes to a mixed inhibitor, what I want you to look for is intersection between the unchallenged and challenged data lines where the intersection is in this quadrant number 2. So remember, that was not a very straight line. Remember our quadrants, 1, 2, 3, 4. If you have your lines intersect within quadrant number 2, you are talking about a mixed inhibitor. So what this inhibitor is capable of doing is actually fairly complicated because the free enzyme can bind to the inhibitor, leading to the EI formation. Alternatively, if the enzyme binds the substrate, you lead to the formation of the ES complex. Now, with this specific inhibitor, with this specific type of inhibitor, your free inhibitor can bind to your enzyme substrate complex, leading to the formation of ESI. Okay? But wait a minute. I just said that this exact same inhibitor could bind to the free enzyme, forming EI. I stand by that. EI, when that is formed as a mixed inhibitor, it can bind to S, which again leads to ESI or EIS. So with a mixed inhibitor, the inhibitor can bind E or ES. Now, its ability to bind ES makes it very similar to an uncompetitive. Its ability to bind E makes it very similar to a competitive inhibitor. Now, to piece all or to kind of make a more comprehensive or complete story, we need to look at the last one, the non-competitive inhibition. With a non-competitive inhibitor, you have an inhibitor that binds to a site other than the substrate binding site. The inhibitor does not change affinity for the substrate or the inhibitor or the enzyme, but the inhibitor can alter catalysis. Now, what this looks like graphically, purely non-competitive inhibition is where you have intersections on the x-axis. So what does this mean? So when it comes to understanding all these different kind of levels of um, inhibition, what I think is good to do and what I think is best is to recognize that, hey, a mixed slash non-competitive inhibitor, non-competitive, in theory, is capable of binding to the free enzyme or the ES, leading to EI or EIS or IES, ESI. Now, when it comes to distinguishing a mixed inhibitor from a non-competitive inhibitor, though, what we need to look at is where do the lines intersect? So the way that I think is helpful to think about it is to grab the X and Y axis and give yourself a red line corresponding to unchallenged. Okay, so that's no inhibitor present. And then switch colors and basically give yourself another line representing a different inhibition data. So now I've switched to a gray line, a light gray line. This is plus inhibitor. Could anyone tell me in the chat what type of inhibition is represented by this gray line? Competitive. So if you were to see this right here, that's a competitive inhibitor. That's what a competitive inhibitor does. Then to think about, well, what happens to your Km and Vmax? Km goes down, Vmax unchanged. Now, my next line, I'm going to use a purple line. Now that's drawn decently. This is uncompetitive inhibitor. These two lines are parallel to one another. Whenever I think of an uncompetitive inhibitor, I think of my unchallenged and challenged data basically being parallel. So my lines aren't drawn perfectly, but that's what I'm trying to display there. What happens to my Km? From this point versus this point, my Km, well, it goes up. What happens to my Vmax? Or sorry, my Km. Oh, sorry, I did that backwards. Uh, with a competitive inhibitor, my Km goes up. With an uncompetitive inhibitor, my Km goes down. With, I'll do it here. My Km here for an uncompetitive inhibitor goes down. What about my Vmax? My Vmax goes down. Now, sorry about that confusion there. My next data set is, well, what if I have, I'm going to switch colors one more time. Let's go with sky blue. I have a line like this, plus I. Okay, here my intersection is not on my y-axis. The two lines intersect, but it's not on my y-axis, so this inhibitor is not a competitive inhibitor. This instead is a mixed inhibitor. Okay, so then what happens with a mixed inhibitor to my Km and my Vmax? Well, my Vmax, what happens to my Vmax? Okay, it went from this point right here to this point right here. So my Vmax goes down. What about my Km? Well, it got steeper, therefore my Km goes up. That's what a mixed inhibitor is going to do. Now, last but not least, we've got a green line. And again, I'm comparing this to my red unchallenged line. And for this one, I'm going to go from here to here. And I'm sorry, I've got lots of data points displayed there. But what do I know about my Km? What do I know about my Vmax? My Km, unchanged. But what about my Vmax? Well, from here to here, that number goes up, but it's a reciprocal value, so my Vmax goes down. Now, what you can do with this is obviously draw these kind of independently, or look at a plot like this, where I've just kind of pinpointed what's happening to your different kinetic parameters, your Km, your Vmax. Where are your intersections? And write those out. So competitive. Then we go straight down, mixed. To the right, that would be non-competitive. Then straight up would be uncompetitive. I think that it's in your best interest to see those plots and be able to decipher and like identify each one. See the plots, identify each one, and then from there, fill in those hypothetical numbers and calculate your Vmax and your Km respectively. Now, with that in mind, it's also helpful to, you can make a table that says what does each one of them do. It's also helpful to think about the complexes. With an uncompetitive inhibitor, will you form ES? Yes. Will you form ESI? Yes. Will you form EI? No. Okay, I got a private message. What's the difference between non-competitive and uncompetitive? Okay, so the difference between non-competitive and uncompetitive is what does this inhibitor actually do to the enzyme's ability to bind its substrate with a non-competitive versus an uncompetitive inhibitor. And um, your non-competitive inhibitor, the affinity for the substrate is unchanged. But the rate of the reaction as it's catalyzed is going to be changed. In addition to that, a non-competitive inhibitor, so I'll put it this way, Km Vmax, and then Km Vmax. For a non-competitive inhibitor, Km is unchanged, your Vmax goes down. Km for an uncompetitive inhibitor goes down, Vmax goes down. Now, in addition to that, when you look at a non-competitive inhibitor, will ES form? Yes. Will ESI form? Yes. Will EI form? Yes. All of those are capable of forming, whereas an uncompetitive inhibitor, EI cannot form. So I think one of the biggest tricks is to look at the different complexes, ES, EI, ESI. And again, ESI, EIS are the exact same. Do they form? ES, EI, ESI. ES complex with a competitive inhibitor? It does. EI? It does. ESI? It does not. With a mixed inhibitor, ES forms, EI forms, ESI forms. So then, you could think about, well, what's the difference between a competitive and an uncompetitive inhibitor? The difference between these two is ESI formation or EI formation. So if I were to, there's your difference between those two. With a mixed inhibitor or a non-competitive inhibitor, ES forms, done. ESI forms, done. EI forms, EI forms. Well, how do we determine the difference between these two? Well, that boils down to what happens to your Km and what happens to your Vmax. You can see here that your Km, your Vmaxes will change, same thing, but what about your Km? How is that going to change? And that would be something where you just plug in some numbers. You scale up a plot like what I'm showing you right here, and you say, all right, well, here's my X and Y axis, unchallenged, and I never, yeah, and then here is challenged. So this would be unchallenged would be, let's call that 2, -2, and then -1.5. Okay, so -1/km equals 2, -1/km equals 1.5, -1.5. So I'm looking at km equals 0.5, and then km equals 1 divided by 1.5. Calculator. 1 divided by 1.5, and that would be 0.67. And my kids aren't here to hear me say 0.67 and then say, that was so 2025. So there we go. So Km for when we look at a mixed inhibitor versus a Km for a mixed inhibitor. So our Vmax is going to go down. That's the same as a non-competitive inhibitor. Your Km, your Km is going to go up, which means a mixed inhibitor will cause the affinity that your enzyme has for the substrate to go down. I think if you took this right here and organized that into a table, that would be very helpful. If you were like, okay, I'm going to start my note card for my next exam and, do a quick sketch of each one of these graphs and then made like a table of ES, EI, EIS. And then say comp, uncomp. That would help you out a whole lot. Okay. Um, so a review for exam 2. Yeah, I will. I'll put some practice questions and stuff out before the actual exam. But on Wednesday, like I said, Wednesday is going to be just kind of a general exam. If anyone has questions about this, we'll do that. Other than that, though, that's where I'm going to stop today. It's kind of catches us up to what I wanted to get us to. Um, Wednesday I'll have pre-recorded stuff, but then Wednesday during our actual class time, I'll be holding kind of a general review, question answer, office hours type of situation. And so with that said, I hope you all have a great afternoon, and I will see you guys on Wednesday. Or if you don't make it on Wednesday, that's okay. Thank you very much for your time and your participation. I hope you guys have a great day. Wednesday is asynchronous for new material, but then during our class period, so at 3:30, I'll be on our regular Zoom. So I'm sorry to not have a clear answer. So for new material, Wednesday is asynchronous. For review, I will be here and I will be recording that. I hope that answers your question.